My name is Gonzalo Morales, and this is my Lab 5 report, Magnetic Braking with Faraday. Introduction. Our objectives for this lab are to observe and predict how long it takes for a bar magnet to fall through a conductive tube of aluminum foil, model the magnet-tube interaction computationally, and compare the computational predictions with our observed data. Some of the fundamental principles that we will be using are Faraday's law and Ohm's law. You can see it here, and it calculates the current induced in each ring by the falling magnet. We're also using the Biot-Savart law, which calculates the force exerted on each current-carrying ring by the falling magnet. And we'll be using Newton's second and third law to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings. And the third law to write the position and velocity code to model the trajectory of the falling magnet. This is pretty much what the experiment consisted of. First, find and mark the end of the magnet. Then drop the magnet through the tube of aluminum foil and film this with our phone to determine how far down in the tube the magnet went. Repeat 5 times to determine the average time the magnet spends in the tube. And here we can see our data. The magnetic moment was 2.87 am to the third. The mass of the magnet was 0.023 kilograms. The length of our tube was 0.305 meters. The width of the aluminum foil was 0.005 meters, and the radius of the tube was 0.02 meters. And you can see after our 5 trials, we had an average of 1.14 seconds of the time the magnet spent on the tube. Here you can see our code. First, this is the code we use to initialize constants and create a graph that displays velocity of the magnet versus time. Then this is the part of our code that creates a hollow tube to represent the aluminum foil tube. Here we created a cylinder to represent the bar magnet and initializing time and velocity values to 0. These are functions that calculated the magnetic field of the bar magnet and the magnetic flux on the foil due to the falling magnet. And this is our code to calculate the gravitational, magnetic, and net forces on the magnet. And also this part of the code updates the magnet's position and velocity and calculates the amount of time the magnet is in tube and prints the total time. Here we can see our computational model. The magnet falls through the tube, inducing a current as it falls. The graph displays the velocity of magnet in tube over time. And the model calculated the time that the magnet was to be in the tube to be 2.763 seconds. So now we have to interpret the model, and changing the magnetic flux due to the falling magnet induces currents in foil tube above and below the magnet. The red line is the clockwise current and the blue line is the counterclockwise current. A flipping magnet around reverses the direction of the current because of magnetic flux will be changing in the opposite direction. The magnet's speed changes rapidly when it first enters the tube. The velocity then remains constant in the middle of the tube, meaning the net force is 0 while the magnet is falling inside of the tube. The magnet reaches a terminal velocity in the tube at this point, and then the total time in the tube of our experiment was much smaller than the computational model. In our experiment, the average time was 1.14 seconds, and in the computational model, it was 2.763 seconds. So now the final questions of the lab. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, the braking force increases to a point where it balances the gravitational force and prevents the magnet from falling through the tube altogether. And then what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? This would disrupt the normal flow of current through the rings of current in the tube. What would likely happen is that the braking force would not be as strong due to a reduced amount of current being able to flow through the tube. Thank you. Thanks for watching.